This question is about isomers. Hex-2ene has the molecular formula C6H12. Draw the displayed, so we need to be careful about that, that's just like trying to catch us out, of a position isomer of hex-2ene. So we need to move the double bond so it's not on number 2. That exists as E and Z, which means we can't draw hex-1ene, because if we were to draw hex-1ene, hex-1ene doesn't have E or Z. So the next possibility would be hex-3ene. So if we were to put the double bond on number 3, so we would have 1, 2, 3, 4, 5, 6, this structure, but we have to do displayed formula, so every atom and every bond would have EZ isomers, and you can see that I've drawn the Z isomer here, but we don't have to draw both the E and the Z, we just have to draw a position isomer that has EZ. So hex-1ene wouldn't, hex-2ene was what we already had, so we move it to hex-3ene and we have got EZ isomerism. Draw the displayed formula of a chain isomer of hex, we're still on displayed, of hex-2ene that does not exist as E or Z isomers. So chain isomer needs to be like pent. So let's try to do a pent-2ene. So if we were to do a pent-2ene, so that would be a chain isomer of hex 1, 2, 3, 4, 5. And then we would need a sixth carbon. And if we want it to not have EZ, if we were to put it here, then we would have 2 identical groups on one of the carbons of the double bond. And we can see that by drawing this structure, 2-methylpent-2ene, we don't have EZ, but we are definitely a chain isomer of hex-2ene. Now there is another structure that you could draw, so you could also draw a but-2ene, and if you want to draw a but-2ene, you would end up with, this is but-2ene, 4 in a row, you'd end up with all these as methyl groups with all the hydrogens drawn out. I'm not going to finish that off, but that would also be a chain isomer that doesn't have EZ. Butanal has the formula C4H8O, so we want a functional group isomer of an aldehyde, so not an aldehyde, but we still have to have a C double bond O because of that absorption at 1680 to 1750. So if we're not going to have an aldehyde, we want to have a ketone. They are functional group isomers of aldehydes. So we're going to look for a ketone, and it's asking for a skeletal formula. So instead of having butanal, we can just have butanone, and we draw that as our skeletal formula. Draw the skeletal formula of a structural isomer. So again, we're going skeletal. Structural isomer, so chain, position or functional group. This time it needs to be an alcohol. So because of the 3230 to 3550, we need an OH in alcohol. So we are going to need to change the functional group from aldehyde to alcohol, but alcohols tend to be saturated, and to have the formula C4H8O, we need some level of either unsaturation or cyclic nature. So we could draw the cyclic alcohol, but we could also draw an enol, and there are lots and lots of possible answers here. So you could have 1, 2, 3, 4, and then start putting the OH in different places on this structure, all sorts of different places. There's going to be, like here, you could go like here and so on. So you can move it around. You could even branch that. You could make a triangle with your alcohol and a methyl group. There's lots and lots of possible answers here. Several saturated halogenoalkanes, so CnH2n plus 1x, so where X is the halogen, contain, and we've got some percentages, and we've been asked to calculate an empirical formula. So let's convert our masses, 17.8, 3.0, and it's BR, 79.2. Let's convert mass to moles by dividing by the MR. So if we do that, we'll get 1.48, 3.0, and 0.99. And then if we divide by the smallest, we'll get 1. And when we divide this one by 0.99, so if you do 1.48 divided by 0.99 on your calculator, you get essentially 1.5. And here you get essentially 3. So we need to multiply until we get whole numbers. So 3 to 6 to 2. So C3, H6, Br2. So that's our empirical formula. And it says give the names of 2 saturated, so no double bonds, halogenoalkanes that have this empirical formula. So we're trying to think about 3 carbons, so 1, 2, 3, 6 hydrogens, 1, 2, 3, 4, 5, 6, and 2 BRs. So we could put the BRs on the same carbon, number 1. We could put 1 on number 1, 1 on number 2. So we're looking for things like 1,1 dibromopropane, that's the one I've drawn. But we could have 1,2 dibromopropane. We could have 2,2 dibromopropane. So 1,1 dibromopropane is, we'll just rewrite that. 1,2. We could have 2,2. We could have 1,3. So just be careful, there's lots of different possible answers.